Here is an example of lifetimes of bulbs. The lifetimes of light bulbs were recorded by running them at a high stress so that 1 hour of lab time is equivalent to 1 month of life at normal use. It's a kind of a specialized experiment. We got the data from this experiment. Okay, so these are the numbers. So to give them meaning, we first develop a frequency distribution. The frequency distribution data is here. And our objective is to see whether this data can be approximated by an exponential distribution, because an exponential distribution seems to fit the failure data of components, and it is governed by one single parameter, the lambda value. Exponential functions are simple. They are readily used for the operational life of components. So I copy this data to a Microsoft Excel sheet. Here it's open. Okay. And the okay. So a bit larger font size would be nice. Yes. So frequency and all that. We can get the total number of components. So it's a simple summation of these numbers. So 100 was the number. We can compute the relative frequency which was equivalent to probability. Relative frequency equivalent to probability. So all the numbers in frequency must be normalized by the total number. So we have 100 as number. Relative frequency, it is equivalent to probability, and it is equal to frequency divided by the total number n. So I can take the number from its respective cell, $12, so 0.57. So we have got these numbers, relative frequency or the probability. Right. So for taking the time value, we have considered class mark. So the number 57 bulbs failed from 0 to 100 months. So that's the interpretation of class mark and all that. So this is the relative frequency function, and this is when plotted with the upper limit of time. For the first one is 100, for the second one is 200. If I plot this one, the upper limit of the interval, these are the upper limits. And if I go for the cumulative distribution, that how the frequencies were, how the probabilities were added to the next classes, if I take the first value as such, this is the time value in months and the upper limit of the class. And here, how many components, how many bulbs have performed a lifetime up to 200. So this will be the upper value plus the relative frequency here. So that is the probability. And this probability is going to saturate. Right. It saturates at 1. This is the function as the cumulative distribution function. With respect to exponential distribution, we know this f of t is equal to Well, I should write here somewhere here as how to add equation. Okay, let's pick the equation from these slides. So the f of t is 1 minus e raised to the power minus lambda t, right? So we can define r of t. That is a simple one, 1 minus f of t. So it is simple. Probability of components surviving to the time limit. So that is complement of t. But this is very nice. If you plot the values with this one, it is very simple to get the relationship. So, for example, if I take r of t is equal to e raised to the power minus lambda t. This is exponential relationship. So if I take, for example, log of this equation, log of r of t. So this is equal to natural log of this one. So a negative value, fine. Well, log of 0 would be infinite. So therefore, from the data, I can use the earlier values. So now let's plot it. Well, there is some problem with the Microsoft Excel. Some of the tabs have been lost. How to get to that one? It is hidden. Plot the data. Not everything. I would like to plot time and the r of t. So remove all the things. Add a series, and x values are the time values. We'll skip the last value since there is infinite value there. Right. And then on y-axis, log of r. So we have got approximately for first part, we see that there is a straight line, right? If we see this straight line closely, let me try to write the equation from here. Okay. That log of r of t. If I take the log, so it turned out to be minus this lambda value times t. It means if we plot log of r versus time, it will be a straight line with the slope equal to lambda, right? With the slope equal to lambda value, and lambda is the value which is the parameter of exponential distribution. If the fitting is fine, criteria which comes from regression. If you apply the regression here, I can do that one right here. If you do the regression, right, between log of r and time, so in Microsoft Excel, you can add a trend line. So trend line of type linear, y equal to mx plus c, and I ask it to write the equation on chart and also display r squared value, which is a measure of goodness of fit. So if you carry out the regression analysis, then we find the slope value, which is in our case the lambda value, let me increase its font, right, and give it a color, right, so that it is visible. We find r square value is 0.94. R square value is closer to 1, it means the model is close to perfect model. So it means lambda x, lambda value is somewhere closer to 0.061. 0.061. So let's develop a probability distribution based on model with the value 0.061. Right. Drag it somewhere. Right. Now I compute f of t, which is from theory. So from theory, I can compute is equal to 1 minus e raised to the power minus lambda times t. So lambda value is 0.0061 times the t value, which is 100 here, right? That's it. So I got 0.4566 and so on. Similarly, I can go for further calculations. So f of t, we have this column, f of t, this column and this column. F of t, this column is from the experimental value, and f of t theoretical are from the model values. So you can see there are differences. How significant these differences are, this is something that we will study in the later part of the course when we study the goodness of fit.